All right. Hello, my name is Quentin Odenthal, and this video is my submission for for my part of the first group assignment for Computer Science A311. I'd like to start by saying that while I was doing some research for my part, I came across this proof that worked for my questions, a really intuitive proof, and I really liked it. And I used that proof, which is from geeks4geeks.com, which I'll have the link for that article or whatever it is in the description, and I also used the notes and the reading as references. Okay, so on to the proof. So let's prove that, um, that's not a brush. Let's prove that the max of two functions, oh god, this is not going well, f of n and g of n is equal to, is theta of f of n plus g of n. So that's what we're trying to prove here. Take that, scale it down, put it up there, if you can read that. Okay, so let's start with a definition for theta. Theta. So theta of gn, actually it'd be better to start with this. Let's move that off into the abyss. So we got f of n here, let's say, and that is equal to theta of g of n, got lucky with the parentheses there, when there exists three values, C1. Did I really just do it backward? I did just do it backwards. See, how is that possible? Okay, wow, cool. And there exists correct C1, C2, and N0, where um, 0 is greater than or equal to 0 g of n times C1, which is less than or equal to our f of n, which is less than or equal to C2 times g of n again, for all n greater than or equal to n0. 0. That's a 0. Yeah. All right, so that's our definition for theta. We just need three values, C1, C2, N0, where if you multiply Gn by C1, it's less than Fn, and if you multiplied C2 by Gn, it's more than f of n, for all n greater than or equal to N0. So try to save that. I don't know how readable this will be when I minimize it. That's our definition. So let's start with, well, if we prove, wait, hold on. And if we apply this to our problem specifically, our theta of gn would become theta of f of n plus g of n, which means we need this, f of n plus g of n, put some parentheses around that, multiply it by c1, less than or equal to max of f of n, it's not a t, and g of n. And then that's less than or equal to, I guess I'll just put it right here, C2 times our f of n. Oop, okay. Plus g of n. That's a little messy, but. And then for all n greater than or equal to Rn0. So that's when it's applied to our problem specifically. So I'm going to move that away and then take all this and put it small, put it up there. Perfect. Yeah. So if we can find three values, C1, C2, and N0, where they're all valid and this all works, then we've proved that, that's not a brush, we have proved that the max of two functions f of n and g of n is equal to theta of f of n plus g of n. So let's try to do that. So now let's start with finding n0. And it's kind of less about finding n of 0 and more of just picking one, because you have a lot of options for n of 0. So let's choose one that is useful for us. Let's see what I wrote down here. So if we assume, let's start by assuming that f of n, let's make it red, is a function like that, has that growth rate. And let's assume that g of n is like maybe linear or something like that. So if we assume that f of n has the greater growth rate, more intense growth rate, then we know, I'll put this in black again, we know that right here where they intersect, f of n, or after this point, going that way, f of n will always be greater than g of n. It'll always be above it. And that means that this max function that we have, f of n, g of n, will always equal f of n for all n greater than or equal to the point where this thing intersects, which we could set as our n0. That's a valid n0. So if we choose n0 for right there, then we know that this is true, which is really useful for us. So let's make n0 equal to the intersection of f of n and g of n, where we could just, we don't actually know what the functions for f of n and g of n are, so we can just assume that one of them is greater than the other one, or if they're equal, this still works, because max would be equal to both of them at the same time. So where f of n is, yeah, where f of n is greater than, I don't actually need to put that. I'm gonna, it's equal to the intersection of this. So let's put this guy right below here. Maybe shrink it down a little bit. Alright, so we've picked our n0. That's a useful n0. It's at the intersection of these. I might keep this graph around. It's kind of nice to see. Put it down here. Take this. Go away. Oop. Let's take that. Go right over here. And then let's go back to our brush. And this is 0. It's right at that point. Okay, so we've picked an n0. It's a good first step. So let's now go on to C1. Let's find C1 next. So C1 needs to be a value where C1 times our f of n plus g of n is less than or equal to our max. Getting kind of sick of writing this. For all n greater than n0, right? So we need to find our C1 where this works. So we know, since we picked a useful n0, that for all n greater than or equal to n0, f of n, right here, is greater than or equal to, actually, our g of n, right here. We know that that's true, which means that our max function equals f of n for all n0, or n greater than or equal to n0, which means that we know, well, I guess that doesn't, hold on. So that, which means that's equal to f of n, right? We know that that's true. And we know that since g of n is less than or equal to f of n, we know that our g of n plus f of n, right here, is less than or equal to f of n times 2, right? Because at the very least, or at the very most, these guys are the same, equal, and if not, this is less, right? And if you do a little bit of algebra, we could just pop this over and make it 1/2. Then we know that 1/2 of f of n plus g of n is less than or equal to f of n. And we know that f of n is equal to max, which means 1/2 of f of n plus g of n is less than or equal to max of our stuff. I'm not gonna write it again, I've wrote it a million times. And that's exactly what we were looking for, where C1 in this case equals 1/2. So we can pick, that C1 equals 1/2. We know that's a valid C1. We just went through all the math and proved it, right? So boom, we found C1. Let me take C1, move it, shrink it, put it up in our corner. And let me clear out. Is there anything useful I want to keep? No, we just went through and proved. Yep. Now we know what C1 is or can be. Picked a valid C1. Go away. All right. Let me look through my notes here for a second. Let me see. Yep. 1/2. Yeah. So 1/2 is a valid value for C1. Nice. Let's go on to the last thing we need to find, which is C2. And now the logic behind finding C2 is actually pretty similar. We know that we just went through and, or we know that max of our stuff. I guess I should write it if it's not on the screen. One more. One more. Come on, thank you. Max of f of n and g of n. We know that this equals f of n for our n greater than or equal to n0, all n. This one. So we know that that's true. And since that's true, or not since that's true, we also know that f of n plus anything is greater than or equal to f of n. I guess anything that's not negative is greater than or equal to f of n. And what we're looking for in C2 is times our f of n plus g of n greater than or equal to our max, which is equal to f of n. Right. So we're trying to find some value C2 where this is true for all n greater than or equal to n0. And since f of n plus anything is greater than f of n, we know that f of n plus g of n is greater than or equal to f of n. So we don't need to even multiply anything except for a 1. So C2 can just equal 1. And that's our valid value for that. So C2 equals 1. And now that we have all, make sure I'm not deleting anything useful here. And now that we have all of our the 3 values that we need for those, we can prove this right here. Oop, brush. We can prove this with this equation right here. So the max of f of n and g of n is equal to theta of f of n plus g of n, where theta of f of n plus g of n is equal to 0, which is less than or equal to 1. Let's do this. This is a nice way of doing this. Brush. So we got C1 times f of n plus g of n, which is less than or equal to our max, which is less than or equal to C2 times f of n plus g of n, where C1 equals, wow, C1 equals, oh, come on, equals 1/2. I just crossed it in half, but equals 1/2. We proved that. Where C2 equals 1 and N0 equals the intersection of those guys. Intersection of f of n and g of n. I think I forgot to, yeah. So 0 less than or equal to C1 times that, which is less than or equal to max, which is less than or equal to C2 for all that. For all, forgot to write this down, for all n greater than or equal to n0, where C1 equals 1/2, C2 equals 1, and N0 equals the intersection of these two functions. And then, boom, that's a valid definition right here. This is what we needed to prove. And we have all our values that are valid. And now we have proved that this up here is true. And now it's proved. And there's the proof. And I got most of this function, or this proof, I mean, is really similar to the one that I saw on that Geeks for Geeks website. And that really helped me understand how this worked. And so if you want help understanding that, you could go check out. I'll have the link to that website in the description, but that's the main resource that I used for this proof. But yeah, there's the proof, and there you go.